So today I want to finish the discussion of loops. Now directly from the perspective of the amplitudes. And we've already given a definition of the all-loop amplituhedron. And if you remember, in the definition, there was a motivation for this extended notion of positivity coming from hiding particles, from giving us a different notion of positivity from the Grassmannian point of view. And I want to, so that's a standalone definition. In principle, the claim is that you're done. Okay, so that the space is defined for the all-loop amplituhedron. If you compute its canonical form, you'll get the loop integrand. But I want to give some more intuition for where this comes from directly from the perspective of the amplitudes and complete the formula for the all-loop, the extension of BCFW recursion relations to all loops from this point of view. I'm going to have to be a little sketchy in some parts today, but I think you'll see the concrete formulas and the motivation for why they're all true. I hope will come through. If I wanted to do this part in complete detail, I think it would just take sort of just one more lecture. But I would rather spend the time telling you about some other sort of qualitative things. Okay. But so let's first begin with the kind of zeroth order idea of where we're getting loops at all. And so that's this idea of hidden entanglement. And what do I mean by that? Well, imagine that we have some amplitude, or maybe a piece of an amplitude, an on-shell diagram, something. And let's say that there's a bunch of particles, 1, 2, 3, up to n, and there's one of them, A, and I want to get rid of this particle. I want to ignore this particle. Okay. So whatever this object is, it might be an amplitude, it might be something else. Let me just call it m, as if it's an amplitude. Okay. So this depends on A and 1 through n. And what do you think you can do in order to get rid of the dependence on A, to ignore A? Well, if someone hands you this function, it's a function of, these are all momentum twistor variables. Okay. The most obvious thing to do is to just integrate over A. So I want to hide A just by integrating over it. And so what am I going to do when I do the integral over it? I'm going to do the integral d4/4 ZA. Okay, so I have to integrate over the bosonic and fermionic components of A. And remember, there's an overall GL1. Everything is little group invariant, so I should really do this. Okay, so that's kind of an obvious thing that I can do. Okay, I could write this. I could write this more explicitly. The d4ZA mod GL1, as we've gotten used to, and thinking about things projectively, is a ZA d cubed ZA, and there's still a d4 for the eta component. Okay, so this is some calligraphic Z for supersymmetric, but this is just the ZA and the eta A and everything else. Okay. Now comes the question: what do we mean by this integral? Okay, so what exactly do we mean by this integral? What is the contour of integration? Okay, and well, if we're taking objects that we can get, let's say, from on-shell diagrams or tree amplitudes or whatever, then we've seen over and over in this course the only interesting contours of integration that we can talk about take residues. Okay, so this is a function of 3 variables. I can take a bunch of residues, and what will that do? Well, if you just get rid of one particle and you just take residues, so in other words, you perform this integral to encircle singularities of whatever this object is. And this is going to be some rational function of the ZAs, right? If it's an on-shell diagram or a tree amplitude, it'll be a rational function of the ZAs. We'll have a bunch of poles in the ZAs. And so I can just take residues when I get rid of this guy. And I'm going to be left with some other rational function when I'm done. In fact, that other rational function that you're left with when you're done, you can associate it with some other on-shell diagram in some interesting way that just corresponds to removing the particle in a variety of ways. Okay? You can take lots of different poles, and the different poles can correspond to different on-shell, will correspond to different playback graphs, different on-shell processes, and so on. Okay. So if the contour that we take here is just, if the contour that we take is to compute residues, then we'll just go, it's not all that interesting. We go from some on-shell diagrams to some other on-shell diagrams. OK, but there's something more interesting that we can do, and I'll illustrate it with an example. There's something more interesting that we can do when we have a pair of particles. Okay, so let's say I have a pair of particles, ZA and ZB, 1, 2, up to n. Then I want to do this integral, d4/4 ZA, d4/4 ZB, modulo GL1 for A and GL1 for B, of some ev of calligraphic ZA, calligraphic ZB, and everyone else. OK, so let's just be concrete. What is the dimensionality of this integral? This is some 6-dimensional integral, bosonic integral. OK? 6-dimensional bosonic integral. But as we're now going to see, there's a natural contour that we can choose for this integral that you can think of as dividing the 6-dimensional integral and doing the 6-dimensional integral in 2 pieces. Okay? First, we're going to do a certain 2-dimensional integral, and then be left with a 4-dimensional integral. So we have a 6-dimensional integration contour, but I'm not going to specify an integration contour by telling you about a 2-dimensional contour of integration and then a 4-dimensional one. So we denote, sometimes we denote this by drawing a curly line, and we call it entangling the particles. So here is the contour. Again, let's think bosonically. So here's ZA and ZB. And in principle, all we're doing is doing some 3-dimensional integral over ZA and some 3-dimensional integral over ZB. So that's the 6-dimensional integral that we're talking about. Remember, all these things are in P3, so this is all a picture in P3, the P3 of momentum twistor space. But we actually want to do the integral. We want to imagine first doing it in the following way. Look at the line that's formed by AB. Okay, and now on this line, I can move ZA and ZB, keeping the line AB fixed. Okay, so you see that there's 2 integrations that I can do that move A and B along the line AB, right? There's 1 degree of freedom for A and 1 for B. So I'm dividing this integral over, I'm dividing the 6-dimensional integral first into 2 1-dimensional integrals where ZA and ZB move along this line. And I'm going to do that integral in some way. Okay? As we'll see, we're going to do that integral on contours by taking a residue, and there's going to be a completely canonical way of doing that integral. So we'll talk about it. But I'm now just specifying what the basic shape of the contour is. First, I'm going to do 2 different 1-dimensional integrals along this P1, along this line, where A and B are on this line. And then I'm going to integrate over the space of all lines. Okay, so I want to so the contour that I want, the entangled contour, so it's obvious why it's called entangled, because the sort of contour, the contour now depends on A and B. I'm not independently integrating over A and B. I'm integrating A and B along the line first, and then integrating over all the lines. Okay, the entangled contour is to first integrate A and B along the line AB. That's 2 dimensions. And then second, integrate over lines over the line AB. And again, what's the dimensionality of the space of lines in P3? It's the same as G24. It's 4-dimensional. That's the loop integral that we're talking about all the time, right? The loop integration is the integration of the lines in AB. So this is 4-dimensional, and it looks like a loop integral, or a loop integrand. So in other words, loops are literally going to come from integrating out particles, but integrating them on this interesting contour, where we first integrate along the line AB, and then the loop variable is going to be the line left. So another way of saying it, sorry, I'm saying the same thing over and over again. What are loops? Let's just back up. What is the sort of loop integrand? Is that my data is a bunch of momentum twistors, Z1, Z2, up to Zn, and then I have some bunch of lines. Like at one loop, I'd have some line AB. So this already looks kind of funny that in momentum twistor space, we have 2 different kinds of things. We have the points, Zs, and then we have the loop integration variables that are lines. Okay? And the claim is that this all comes from something where everything was points to begin with, including some A and some B, Z1 to Zn. But I am forgetting about, I'm integrating A and B along the line and forgetting I'm integrating these guys in some way. And the active integration, after I'm done, I only remember the dependence on the line AB. I only see the dependence on the line AB through Z1 through Zn. Okay, so just saying, I've said the same thing now five times, basically the same way. I don't know why I did that. Okay, so, okay.
Is this reversible? Can you take?
No, you're forgetting. So so you can't go back up from an AB and randomly plonk two points down on it. Okay, so it's really, you're really losing information, right? So, okay. Now, before we do anything fancy, let's just see how this has a chance of working. Okay, so I want you to see how we can go from something tree to something loop. How do we go from something tree-y to something loopy? So let's say I'm trying to get, so an example. We're not being systematic here or anything. I just want to give you an idea of how we can get something loop from something tree. So we know that for n equals 4, one loop, what we're supposed to get from many points of view is this simple box, which is d4za, d4zb, modulo gl2. And then we have this 1, 2, 3, 4 squared over ab 1, 2, blah, blah, ab 4, 1. And what I want to now show is how we can get this. In principle, we're integrating. So, but there's a form, which is just that 4, 4, 4, right? Now, I want to see how we can get this from something kind of tree-like. So what do I want to start with? I want to start with something that has an extra A and a B in it. 1, 2, 3, 4. And what k should this thing have? The k that it should have should be, when I integrate out the a to a and the a to b, I want to go down to k equals 0. So this thing, whatever it is, should start off at k equals 2. Okay, so this should be something 6-point and k equals 2. Now, fortunately, 6-point k equals 2 is exactly anti-MHV, MHV bar. Okay, so we know exactly what this amplitude is. And this is some delta 2 times 4, some eta stuff, some c dot eta. But then just written in, so this is some delta 2 times 4 with some eta stuff. But downstairs, it's just all the cyclic minors. Okay, so this is just, in this case, it would be AB 1, 2, just all the consecutive ones. B, 1, 2, 3, 1, 2, 3, 4, 4, A, B, 1, A, sorry, 1, 2, 3, 4, 2, 3, 4, A, 6 poles downstairs, right? 3, 4, A, B, 4, A, B, 1. So that's some 6-point object. I'm not going to bother writing the deltas explicitly because we're just going to integrate over the etas in a second anyway. So let's see what happens. So when I first take d4 eta A, d4 eta B, those delta functions are gone, and I'm just left, those Grassmann delta functions are gone, and I'm left with something that looks like 1 over AB 1, 2, just copying down those poles again, B 1, 2, 3, 1, 2, 3, 4 is boring downstairs, but anyway, okay, just leave it. 2, 3, 4, A, 3, 4, AB, 4, AB, 1. All right, so now let me describe. And so now what I want to do is I want to further do some ZA d cubed ZA, ZB d cubed ZB integral on this guy. Okay? And do it on this entangled contour. Now, actually, if I don't do it on an entangled contour, what am I going to get? So let's say I just do an integral over A's first. Just by, how can I do an integral over the A's? I could do an integral over A because, for example, everything is linear in A. Everything in A individually is linear, so I can certainly take a residue where I put 3 of these poles to 0. Okay, and if I do that, I'm just going to be left with something that now has 3 poles in B, and I can take residues in everybody, and I'm just going to get 1 if I've normalized things correctly. Okay, so that shows you already, this is the rational function of A and B, but if I take any obvious contours where I just integrate over A on residues, and then I integrate over B on residues, I'll just get 1. Okay, so this is not interesting. Okay, but now instead we're going to do the integral over this entangled contour. And let me first say it just super explicitly, so you see there's nothing fancy going on, just super explicitly, then we'll say it very slightly more abstractly. Okay? And the second way will actually be more computationally useful as well. But in this case, it's easy enough. We can just be super explicit about the contour. So how do I write? And if I have A and B, I want to parameterize A and B such that this line AB is fixed. Right? So remember that line AB corresponds to a point in space-time, x, right? So AB is associated with a point x in space-time. And therefore, a parameterization of ZA and ZB is simply the following. ZA is equal to, just going back to our twistor correspondence, is lambda A and mu A. But I want this to lie on the line x. So mu A is equal to x lambda A. X lambda A. And ZB is lambda B and x lambda B. Is that clear? So ZA and ZB, so my parameterization of the Z's is now lambda A, lambda B, and x. X has 4 degrees of freedom. Lambda A and lambda B each have 2 modulo GL1. Okay, so we get 1 for lambda A, 1 for lambda B, and 4 for x. Good. That's our 6 degrees of freedom for ZA and ZB. Okay, and so what's the measure? Well, the measure is ZA d cubed ZA. This is very simple to work out, but we can also see it very easily just from weights. ZB d cubed ZB is equal to lambda A d lambda A, lambda B d lambda B. So these are now 2-dimensional lambdas. So they're just 2 different P1s, lambda d lambdas for each one of them. lambda A lambda B squared times d4x. Okay? You see there's nothing else it could be. It has to have to have a d4x. X doesn't carry any little group weights. So this is what it looks like. I have to have a lambda A, d lambda A, lambda B, d lambda B. This makes up the weights so that both the left and the right have weight 4 in A and B. And then there's the d4x. Okay, and so that's it. Now I have to look at this. Integral. Okay, so what is that? And let me also remember that ZA, ZB, JJ plus 1, or J minus 1J, is equal to lambda A, lambda B. This is also just part of our twistor correspondence. J minus 1J, X minus XJ squared. Okay. So what I'm left with is d4x. So I'm just writing out the measure. And then I have just taking that formula, x13 squared, x24 squared. This is just the 1, 2 coming from the 1, 2, 3, 4s. The AB12, AB34, and AB41 just give me x minus x1 squared, x minus x2 squared, x minus x4 squared. And I'm left with 1, 2, 3, 4, 2, 3, lambda A, d lambda A, lambda B, d lambda B, over lambda A, lambda B, ZA, 1, 2, 3, and ZB, 2, 3, 4. I think all the weights work out properly. Yes, 2 and 3 are repeated upstairs, so that cancels. So, okay. Okay, so I've just written out that integrand. Okay, the 3 factors that just involve ABs are these x minus xi squareds, and then I've just left explicitly the factor that depends on A and the factor that depends on B. Notice that whatever this thing is linear in lambda A, right? Just linear in lambda A, so I'm just going to call this thing lambda A some psi A. Whatever this thing is linear in lambda B, so I'll call this lambda B psi B. Okay? And so somehow, so now I've written my contour, right? I've written the integral. It's got d4x and also lambda A, d lambda A, lambda B, d lambda B. Now I want to do this integral over lambda A and lambda B. Okay, and what answer could I possibly get? So let's just write the kind of general integral that we could have here. So let's say I have in general some integral of the form integral lambda A, d lambda A, lambda B, d lambda B, over lambda A, lambda B, lambda A, psi A, lambda B, psi B. Okay? How can I do this integral? Well, there's an obvious contour that I could evaluate on. I could, for example, take a contour that encircles the pole where lambda A equals lambda B. Let's say I do the first integral, right? What is the residue of that integral? It's going to be 1 over psi A lambda B. Now I do the integral over lambda B. It has a pole at psi B and a pole at psi A. Doesn't matter which one I take. I'm going to get the answer up to sine 1 over psi A psi B. So the only way to do this integral on residues gives you the only answer that it can give, which is 1 over psi A psi B. Okay, so here I've taken it on the residue where lambda A collides with lambda b. Is that clear? And as usual, when you write things projectively, you don't have to think, because the only answer you could possibly get for this just by weights is 1 over psi a, psi b. All right, so that's very nice. So what we're left with is just 1 over psi a, psi b in this case. And psi a, psi b in this case is just equal to so what is so psi a is so in this case psi a, psi b is just equal to AB, the guy that we are missing, AB23, times 1, 2, 3, 4, just by weights, or otherwise known as 1, 2, 3, 4 times x minus x4 squared, x minus x3 squared. Which one do I not have there? Yeah, x minus x3 squared times 2, 3. So the 2, 3 cancels, and I'm left with the integral d4x, x13 squared, x24 squared. These are just numbers over x minus x1 squared, x minus x4 squared, which is just our loop integral. Okay? It just depends on the lines x. It depends on the point x. All right, so that's how you can see just very explicitly that if you do the integral over these 2 points on the contour where x is fixed, and you do the remaining 2 integrations on residues, you go from a tree amplitude to a loop integrand, from a tree amplitude to a loop integrand. Okay, now let me say this a little more elegantly, because here it's not so elegant. We went back and forth from momentum space back to the x space, and so on. So let's say this a little more elegantly. So what I want to do more invariantly, but I'm still doing exactly the same thing. What I'd like to do is parameterize ZA and ZB as some linear combination of sort of 2 like fixed points on the line, AB, up to a general linear transformation thereof. Okay? So in other words, I want to write ZA and ZB as some CA, A, CB, B, CB, A, and CB, B, acting on some, let me call it little ZA and little ZB. Okay, so I want to think about little ZA and little ZB as just being any old ways of parametrizing the line AB. And I'm just writing the general A and B on this line somewhere here, some general linear transformations. A general 2 by 2 linear transformation. Okay. So in other words, I want to consider little ZA and little ZB modulo GL2. Okay, so I'm going to identify 2 little ZAs, little ZBs that differ by a GL2 transformation. And I can write any AB as some, if I gauge fix that GL2 that acts on these little ZA and little ZB, I can write any ZA and ZB as some 2 by 2 linear transformation on those guys. And in particular, that means that I can think about the measure on ZA and ZB, capital ZA and ZB, as capital ZA d cubed ZA, capital ZB d cubed ZB. By the way, if you're a physicist, this kind of thing all the time we do in field theory with Fadeev-Popov methods and so on. And part of the point in this business, and we've seen it over and over again, we have redundancies left, right, and center that we're modding out by. You don't have to go back and do this procedure all the time, write down a 1, blah, integrate, blah, blah, blah. You just do it. And we've been doing it over and over again. So, but formally, there are all these Fadeev-Popov things that we could be talking about. We're just writing down the answer. We're writing down the answer, and we're just writing down the correct, all the correct measures. Even for something as simple as d4z mod GL1, when we write it as z d cubed z, we have done the Fadeev-Popov, right? We're just not saying it in that brutally, pointlessly heavy-handed way. Okay? And here it matters very little because these are all finite dimensional things anyway. But if this all looks like what we're doing is sort of is fixing a GL2, then that's actually correct. So note this is a 6-dimensional measure. But now, clearly, this 6-dimensional measure is a CA, DCA, CB, DCB, where this acts on the AB space, right? So this is in the space of these things thought of as row vectors. Sorry, what am I doing? CA. Okay. Times D4 little za, D4 little zb, modulo GL2. So in other words, this is making manifest that this 6-dimensional measure is where you are on the line times the measure for the space of lines. Okay, so 6 equals 4 plus 2. Right? All right. But now we don't have to go back to X or anything. We just take flat out the object as we're given. And so once again, I get, if I take this thing, it's there's a d4 little za, d4 little zb, modulo GL2. That's what we want to be left with in the end. But now I'm going to have a CA, DCA, CB, DCB. Actually, let me pull out. I have a 1, 2, 3, 4 cubed over. Now notice that ZA, ZB let me just write it. So I get ZA, ZB, 1, 2, ZA, ZB, 3, 4, ZA, ZB, 4, 1. Okay, so that's just from the ABs, because that's just the line AB. Capital AB is the same as the line little za, little zb. But I'm now left with an integral CA, DCA, CB, DCB over CA, CB, CA psi A, and CB psi B, where these things come from the A234 and the B123. Okay, so oh, sorry, maybe I should have written this down explicitly. I think, let me just make sure I wrote this formula down correctly. So it was ZA d cubed ZA, ZB d cubed ZB was d4 ZA, d4 ZB, modulo GL2, CA, DCA, CB, DCB, and then there was a CAB, CB squared. I think I forgot to write that down before. Okay, so there's that CACB squared downstairs. So when I write AB, so AB II plus 1 is CACB times ZAZB II plus 1. So I have 2 of the CACB upstairs, squared upstairs. I have 3 of them downstairs from these terms, so that's how I get the 1 over CACB. And I'm left with a CA psi A and a CB psi B, where psi A is just A234, B234, and psi B is just, sorry, this is ZA234, little ZB234. This is little ZA 123, little ZB 123. Right, is that clear why that is? Because I'm writing ZA like 2, 3, 4. So ZA is CA A little ZA 2, 3, 4 plus CB plus CA B little ZB 2, 3, 4. Okay, so this is CA A CBB times this psi A. Okay, so ZA 234, ZB 234. So that's what I'm calling psi A. Okay? Okay. But now it's exactly the same. Now I just have to do this contour integral. I have to do this integral over CA and CB. There's only one way of doing that integral over CA over CB, and the answer we're going to get so integral of can only be 1 over psi A psi B. What is 1 over psi A psi B? So what is psi A psi B? Is just A1 A234 B123 minus A123 B234. Okay, and what is this? This is just our friend, the Plücker identity, because 2 and 3 are in common to both expressions. So the rest of it is just the bracket A4 B1 minus A1 B4. So this is just 1, 2, 3, 4, AB 2, 3. Okay, just as we saw before. And so, oh, sorry, this is little z's here. Little z. And so I'm left with just what we saw before. Okay, so this integral becomes the integral over these lines, d4za, d4zb, 1, 2, 3, 4 squared over za, zb, 1, 2, za, zb, 4, 1. Okay. Okay, so that's just seeing very explicitly how doing the GL2 integral, so removing 2 particles where we imagine moving them along the line on this interesting contour where we compute a residue, is going to give us, lets us go from something that depends on 2 extra particles as momentum twisters, as points in momentum twister space, and end up with an object that we still have to integrate over, but we have to integrate over the set of lines AB. Okay, any questions about that? Yeah, in this case, if we take those two lines, then we integrate over the space of all lines, and we declare that the lines are, let's say, lines in Minkowski space. Then that's just the normal loop integral. Normal loop integral, and so we went from something tree-like to something that is an integrand that looks like a loop integrand. And if we integrated it where we normally integrate it, we'd get the amplitude. It's divergent, of course. It's infrared divergence, but yes.
Is this a hidden form of the cutting rules?
This is not a hidden form of the cutting rules. This is, it's not directly the cutting rules. Well, I'll come in a moment to what. It's related to single cuts, which are not something that we normally talk about. And single cuts are not entirely. Yeah, it's related to single cuts. The ordinary cutting rules involve cutting more things. But here the sort of conceptual point is a little different. We're not taking for granted to begin with that we have something that looks like it has loops in it, right? I'm just showing you how you can start with something that doesn't seem to have loops in it at all, just has points, and how natural it is when you take pairs of points in P3 and make lines out of them by integrating over them. So if you integrate over them, there's a natural way to take pairs of points in momentum twistor space and turn it into a line where you still have to integrate over the space of lines. So that's going to be the sort of origin of loops in everything that we're doing, okay? And you see this is a sort of more intuitive counterpart directly in the functions that depend on the variables to the slightly more abstract thing that we did with the Grassmannian to remove pairs of columns and go from one notion of positivity to another notion of positivity that we got after we removed the pair of columns. And you notice we treated the columns always in a block together. So that's like modding out by the GL2 that rotates the two columns into each other. So we're seeing the kind of cousin of that operation directly on sort of functions that you could get in momentum twistor space. But I'm just in a moment coming to the interpretation in terms of cuts. Okay, yes?
So this is giving us one loop amplitude or just the entire loop, one loop amplitude?
One loop. This is the one loop integrand for 4 points. So you see that you can think of one loop integrand for 4 points as really being, if you like, thinking about the entire amplitude at one loop for 4 points as just being integrating out 2 particles for the 6-point tree amplitude.
So this is
okay?
integrating out any 2 particles gives me the full one loop amplitude.
That's right. That's right. And you have to be consecutive. So you're hiding sort of consecutive, and it doesn't matter where you put them. That's not trivial. So thanks for bringing it up. I mean, you might think this whole object was cyclically invariant, right? I just hid 2 of them, A, B, but the answer ended up being cyclically invariant to the remaining 4 points. That's very special to this simple case, okay? And for MHV amplitudes, it's very special to this simple case. And in general, we're going to get many more terms contributing to the amplitude. I'm just going to define the single cuts in a second. But the main point I wanted to get in the last half hour is just that there's a natural way of going from things that just depend on points to things that depend on lines, and it just involves doing this integration on this interesting contour where you entangle 2 particles and only keep track of the line that they make. If we do that in a simple case, we go from n squared MHV tree at 6 points to the 4-point loop. More generally, it's going to be slightly more complicated. I'm going to give you the recursive formula for it in general. Okay? Yes?
But like, what question am I asking? Because this is to go to like one loop in some sort of 4-point.
That's right. That's right. That's right.
If I'm saying, okay, I want to know like to some order in some sort of loop perturbation.
Yes.
This 4-point, what makes me add in more points?
I'm just going to describe that I'm just going to describe that now. Yeah. Yeah. Again, this is just sort of meant to be inspiration for how you can get things that where do these lines come from all of a sudden, right? We just have these points in momentum twistor space. At loop level, we have all these lines. Where are these lines coming from? They can arise in this sort of natural way, especially since we have to integrate over the lines, right? That's a cool thing. The whole idea is they have to integrate over the lines anyway. And so you can think of the act of having integrated over the lines. If someone just handed you the loop integrand, you're like, that's weird. There are these loop lines, and I got to integrate over them. But secretly, there's just a bunch of points that I'm getting rid of. That looks much more natural. But it's interesting that I'm getting rid of the points for pairs of them in this entangled way. Okay? And getting rid of points with pairs of them in this entangled way is what is going to give us loop integration, the loop integrand and the process of loop integration. Okay, so the next topic is to talk about single cuts and the forward limit. All right, so for this purpose, let's imagine we just go back for a second and just imagine what some sort of garden variety one loop Feynman diagram might look like. Actually, just like the same one that we drew a second ago, right? So normally, let's forget about twistors, momentum twistors, everything else. Normally, we just say that we have some, let's say some variable here, L, some loop momentum L. Then I'd have L plus P1, and so on, right? Some extra loop variables here. All right, and so we have some rational function of L that we're integrating, the loop integrand, some rational function of L. Okay, but it's clear that we should be able to try to interpret what happens. Already we've seen at tree level that we can interpret what happens when we have poles in the integrand, and the poles correspond to factorization. Okay, so what do you think the poles should correspond to here? Now, there's something that is famous and we talk about a lot. We already talked about it last time. What happens, let's say I draw this same loop diagram, if this is like L1, if this is P1, this is L plus P1, L plus P1 plus P2, let's say. There's the unitarity cut that we've talked about already, and it's familiar from field theory courses and textbooks, where we send L squared to 0 and L plus P1 plus P2 squared to 0. Okay? So if we send L squared to 0 and L plus P1 plus P2 squared to 0, then we know how to interpret this, right? We know that what you're supposed to get is just a 4-point tree amplitude on one side times a 4-point tree amplitude on the other side, right? So it's supposed to be 1, 2, 3, 4, and we're supposed to sum over all the helicities that we could have here and the opposites on the other side, in principle. Okay, so we're supposed to sum over all helicities of two of these guys. Nonetheless, as a statement about the rational function, well, clearly there's something simpler that we could do, which is just set one of the L squareds to 0, one of the internal propagators to 0. So what happens when we just send this one L squared to 0? How can we interpret it? That's certainly something that makes sense at the level of the integrand in any theory, right? I mean, it has some rational integrand, has some pole as L squared goes to 0. And we'd like to interpret what that pole is. And what could the interpretation possibly be? Well, clearly it should look like something like a tree amplitude with 2 extra particles, right? So I just cut this guy open and I have it, yes?
I just have a quick question.
Yeah.
So when we do the unitarity cuts,
Yes.
we have energy flow in one direction.
Yes?
So we have like a theta function of L0. Are we doing the same thing here or no?
No, actually, this is actually an important point.
Yeah.
We are thinking about all of these things as rational functions of L, right? So these are just some, in the end, the integrand is some rational function of L. Doesn't know the signature of space-time you're in, does not know about energy, knows about energy conservation only to the extent that some of the external moment is 0. And when you go on this cut, you have energy conservation. It doesn't know anything about the fact you're in Minkowski space, okay? What it's supposed to do, what the residue of this integrand is when you set these 2 L squares to 0 is something that, again, knows nothing about whether you're in Minkowski space or not. So this is just a totally complex statement. It's true in 2-2 signature. It's true in 3-1 signature. If you're in 3-1 signature, of course, if we make these energies positive and those energies negative, so these are in and those are out, then we can interpret these energies as both being, we can interpret this being as an on-shell process in Minkowski space. We may not be able to interpret it as an on-shell process in Minkowski space, and then that's fine. We've already seen over and over again, the 3-particle amplitude is not something we can interpret as an on-shell process in Minkowski space. The amplitude is 0 there, right? So we're being relaxed about that. We're thinking about all these things in principle as complex or real in 2-2 signature. And in real in 2-2 signature, yeah. So I'm just telling you what the residue is supposed to look like. And the statement is that the residue looks like the product of the rational functions of the 3 amplitudes on the 2 sides. Okay? Okay, so what should we get? So clearly from the picture, it's like we're cutting this open. Now this looks like a tree amplitude. Okay? And so there's some helicity plus here and minus there, say, or minus here and plus there, and all of its friends. But importantly, this momentum is L, and this momentum is minus L. So it's a slightly singular configuration. Okay, it's a slightly singular configuration. It's not a generic tree amplitude. It's some kind of tree process where two of the momenta of the trees are equal and opposite to each other. Okay? So that's called the forward limit. Forward, because you can think of these two extra particles as being equal and opposite to each other. By the way, what is the K of this guy? What does the K of this guy look like? See, I've added one more negative helicity particle. Whatever I had before, one side. So the K of this whole the K of the whole thing is up by 1 compared to the K of the underlying loop, right? So if this is minus, the other one would be plus. If this is plus, the other one would be minus. So the K for the tree is equal to the K of whatever I had at loop level that I cut plus 1. Okay, so if I'm trying to do 4-point the way I've drawn it, then this forward limit, the amplitude would have one extra negative helicity particle in on one side or the other, and so it would be NMHV, 6-point NMHV. So at least intuitively, we're seeing that the forward limit of 6-point NMHV should have something to tell us about the 4-point MHV. Should tell us something about the singularities of the 4-point MHV. Okay, now, so that's this L minus L, and K plus 1, whatever the K was for the loop, plus 1. Now, what is the difficulty with this? Well, if you think about any of the formulas that we know and love for gluon scattering amplitudes or whatever, in this limit, as you take two of the momenta to be equal and opposite, they blow up. Okay, they have all sorts of collinear singularities, and they blow up. So this is an interesting kind of open problem in general, because, and actually Paolo Benincasa back there is one of the people who's thought about this to come up with a way to get around this. But in a totally generic theory, no supersymmetry, nothing like that, there is such a thing as a loop integrand. There is such a thing as the pole of the loop integrand at L squared equals 0. The question is, can we give it an on-shell interpretation? And the obvious on-shell interpretation, which is to sum over all the helicities of the corresponding tree, has a problem because it's singular. Okay? However, it turns out that with any amount of supersymmetry, greater than or equal to greater than or equal to 1 supersymmetry at one loop. I think greater than or equal to 2 supersymmetries at any number of loops, although I have to check whether that statement is true. Certainly for n equals 4 super Yang-Mills, the sum over all helicities of this object is perfectly smooth and well-defined. Okay? If you sum over the bosons and the fermions, the entire supermultiplet, you get a perfectly well-defined object. And with a little bit of supersymmetry, the single cuts, in other words, the residue when you set L squared to 0, is given in the obvious way just by integrating over all the particles that you can exchange with the in the forward limit. So in other words, for n greater than or equal to 2, I think, Susie, the forward limit of the trees, and by extension to any number of loops, the forward limit of loop integrands is well defined and matches the single cut of L minus 1 loop integrands. It matches the single cut of L loop integrand. So if you put some internal propagator on shell, then it is indeed given by the forward limit of the L minus 1 point integrand with one higher k. Okay, so that's one place where some supersymmetry, not necessarily maximal supersymmetry, some supersymmetry is helpful. By the way, what are the things that screw you up? What are the things that screw you up for this kind of? There's a lot of interesting things to say about this, but with no supersymmetry, let's say at one loop, with any amount of supersymmetry at one loop, the notion of the loop integrand is, I mean, it's perfectly fine. It's gauge invariant. Everything is perfect. With zero supersymmetries, already at one loop, there is a little bit of gauge ambiguity in what you mean by the loop integrand. For example, if you do a gauge transformation, you find that, of course, the answer is gauge invariant, but up to a total derivative with respect to the loop momenta. The reason we don't see that in n equals 4 super Yang Mills, let's say in n equals 4 super Yang Mills, the only poles that we ever see look like AB12, AB23, and so on. And so you can't have any total derivatives, because if you have total derivatives, you get squares of those poles, and those are not physical things. We don't have double poles, right? So what's going on with less supersymmetry? Well, with less supersymmetry, you can get additional poles at infinity. That's exactly what's missing with n equals 4 super Yang Mills, as we emphasized, right? So because of dual conformal symmetry, there's no poles at infinity. That's why BCFW is well behaved, and so on. So with no supersymmetry, with like already n equals, with any amount of supersymmetry, you can get additional poles at infinity. So I is this line at infinity, and you can get poles that look like 1 over ABI squared. Those are things, for example, the bubble diagram, this bubble diagram, if I just have 1 and 2, this is a thing that we normally associate with logarithmic divergence, right, with the beta function and so on. Well, what is this as an integral in momentum twistor space? It's again d4 za, d4 zb mod gl2. But now I just have a 1 over ab 1, 2. So let's say I have something like this. Let's make it a more 1, 2, 3, 4. This would be ab 2, 3, ab 1, 4. By weights, I have a 1, 2, 3, 4 upstairs. But now I need 2 more ABs downstairs for this to make sense. And what makes that make sense is 1 over ABI squared. Okay, so when you have a bubble integral, you actually have a form, perfectly fine, but the form has a double pole at infinity. So that's already some indication that we're exiting the world of forms with logarithmic singularities. And that's a big challenge in this whole subject, to connect geometry with physics and amplitudes and all the rest of it. Once there is RG evolution, once there's ultraviolet logarithms and so on, the objects that we have to deal with have things other than simple poles. They have double poles at infinity. And there's a lot of action at infinity. All the UV stuff, I mean, it's very cleanly localized to what's going on at infinity in momentum twistor space. But there's some whole world of things that are taking place at infinity. And in particular, if we go to n equals 0 supersymmetry, we find things that look like 1 over ABI cubed. Now, how could we get 1 over ABI cubed? We get 1 over ABI cubed from tadpole diagrams. Things that you would associate with the cosmological constant problem or the hierarchy problem. Things that we normally set to 0 in dim reg and so on. And yet they're there. At the level of the integrand, they're there. And those 1 over ABI cubes actually represent an ambiguity. Things you can add total derivatives to move that guy around. And even the gauge invariance of the answer depends on that 1 over ABI cubed and so on. Everything, I'm not explaining to you exactly how it works, but I want you to know everything that makes these single cuts slightly ill-defined has to do with this issue. Okay, it has precisely to do with the fact that in these cases, the integrands also contain bad things with these poles at infinity. So it's not unrelated to the fact there's some action at infinity that's obstructing us from being able to associate the cut of the loop integrand with an on-shell process that we can talk about. Okay, so there's a whole world of interesting things to be thought of having to do with what's going on at infinity that we've not sort of touched at all in our entire story this semester, which, again, in my view, is the sort of biggest open physical and mathematical challenge in the subject, is to figure out if there's some kind of geometry associated with these interesting poles at infinity, what encodes the ultraviolet, encodes the renormalization group, encodes all this amazing stuff we normally think about in physics, and somehow ties it to the kind of combinatorial and geometric structure we've seen in the infrared. Okay, so I'm not saying anything about this, just to flag it as a big, big problem, big open problem, and to say that it's not unrelated to this thing that I'm just declaring now. Okay, that essentially the second you have to worry about tadpoles, you're in trouble. Okay, the second you have to worry about tadpoles, you're in trouble, and with the being able to associate single cuts with forward limits. But with enough supersymmetry, certainly with n equals 4 supersymmetry, we're fine. Okay, so end of the coda on that comment. So now let's think about what the forward limit looks like in momentum twistor space. Because that's a very, very pretty interpretation. After all, what are we doing? We're taking our polygon. So we have this. This is our polygon in X space. So these are the momenta, right? P1, P2, P3, and so on. And so what we're doing, so let me draw a picture like this. So let's say this is 1, 2, 3, 4, 5, 6. And so as I approach the forward limit, what am I doing? I'm making a side that looks like that. Right? I'm taking this polygon, and I'm taking some point 7, and 6 and 1 are getting really close to each other, so that this momentum, 6, 7, is nearly equal and opposite to that momentum, which is 7, 1. Okay? So in the limit, it's just some line going in and out. So what does it mean in the limit where 6 and 1 are on top of each other? Well, it means that in momentum twistor space, this looks like the following. So I have 1, 2, 3, 4. Ooh. No, sorry. I want to draw a pentagon here. So 1, 2, 3, 4, 5. And 6 and 7 are on top of each other here. This is Z1. Okay, is this clear? Notice that obviously 6 and 7 have got to be on top of each other because Z6 is that ray. Z7 is that ray. So since those are becoming identified, Z6 and Z7 have got to be on top of each other. But that also is telling me something. It tells me that Z5, Z6. I used to have 5, 6 and 6, 1. 1, 2. I used to have 5, 6, 6, 7, 7, 1, 1, 2, and so on. So this means that in particular the line Z5, Z6 must intersect this line. So there's this interesting line that Z6 and Z7 sort of move along this line and they collide at that point. So there's this interesting line which corresponds to this direction. And that line intersects the line 5, 1. Okay, so in the forward limit, I have that Z5, Z1 intersects Z6, Z7. Sorry, intersects that this line 6, 7. So I'm moving 6, 7 along the line 6, 7. Let me say it another way. To go to the forward limit, first the line 6, 7 intersects phi 1, and Z6 and Z7 are moved to the intersection point. 2, 6, 7 intersect 5, 1. Okay, just captured again in that picture. Okay. Okay, so now we're ready to write the loop level BCFW. And let me remind you for a second what the tree BCFW look like. You remember, so a reminder on tree BCFW. We are imagining doing the shift Zn goes to Zn plus little z Zn minus 1. And so we had the formula that mnk is mn minus 1k. And then we had this the sum over n left and n right, and k left and k right. So we have this factor jj plus 1, n minus 1, n1. M right, 1j, and this intermediate point ij, and m left, ij, j plus 1, n hat j, where n hat j was n minus 1 intersect jj plus 1, 1, and ij was jj plus 1 intersect n minus 1, n1. Okay, and this is just what we got from factorizing on the channel n1 jj plus 1, right? So we had n1 jj plus 1, and remember, where did this factor come from? That factor on the factorization channel, right? So this is telling me the answer away from the factorization. I shift to go from the factorization channel to generic kinematics. That's the whole way that BCFW is working. But on the factorization channel, this came from jj plus 1 n1, right? My factorization is on the channel n1 jj plus 1. And if you remember, the top of the C matrix had 4 non-zero entries that just told you where you were, right? Where you were, what precise place you were on that factorization channel. Notice that this increases the k by 1. So remember that I'm supposed to have that k left plus k right plus 1 is equal to k in this case. And so there's a k left plus k right, and this is increasing the overall k by 1. Okay? All right. So what am I now going to get at loop level? Okay, well, there's going to be some loop level here, L. Here I'll have some L1 and some L2. In other words, I can factorize on 2 loops, L1 and L2, where L1 plus L2 is equal to L, right? So I just can... but I have to have an extra term, the sort of seed for the loops, which is the forward limit of the L minus 1 point amplitude, right? So I have to have something here that looks like the forward limit. So I have to have something here that looks like some forward limit piece for n plus 2 particles k plus 1 and 1 fewer loop. Okay? I'm adding 2 particles, k higher by 1 and 1 fewer loop. All right, so what should this forward limit term be? Well, let's first see. Let's see what the ingredients, what the obvious ingredients are. We're doing this GL2 integral, right? Exactly the contour that we had talked about. So we're going to get something which was k is higher by 2. We're going to integrate out the eta for some a and some b, and we're going to do the remaining 2 of the remaining integrals on the contours, just as we talked about. Okay? So that part I'm just denoting as an integral GL2. The integrals over the CA and the CB will always be done on residues, and I'll tell you exactly where we'll take them in a moment. So, and on this side, I therefore should have something like mn plus 2, k plus 1, and L minus 1 of, and it should now depend. Remember, I'm deforming Zn to Zn plus little z n minus 1. So here's n minus 1, and here's going to be my a and my b. Then 1, 2, blah, blah, blah. Okay? So the a and b are going to be added between n and 1. Okay? So let me write this as n of n plus 2, k plus 1, and L minus 1 of 1. And it should not surprise you, therefore, that since we're deforming n to something times n minus 1, that n will be deformed. And it turns out that a is also deformed. Okay, so let me try to explain what these guys are. Where n hat AB is just n minus 1 n intersect AB1, intersect this plane. So remember, in this lower loop thing, A and B are points. So here's the plane AB1, and so the intersection here is this interesting point n hat AB. And A hat is equal to AB intersect the plane n minus 1, n1. So let's say here's A, B. So this intersection point is A hat. Now, what's going on here? Well, let's remember, what does the forward limit look like? The forward limit itself, again, remember always, BCFW is one shift away from the factorization channel that you're looking at, from the pole that you're looking at. Okay, so it's coming from, at tree level, it's coming from the factorization, and then you deform away by one variable. And now as we move around along this line, in this object, we're also going to encounter poles that hit A and B, right? So I can have things like N1 AB, for example. Okay? And so I'm going to hit all of these. Poles. But what does the forward limit itself look like? The forward limit itself looks like on the forward limit itself, I have Zn and Z1. So on the forward limit, where AB N1 goes to 0, So remember, these are the poles that we're talking about, right? So I can have poles involving n minus 1 n in something, but those aren't being shifted under this shift. I can have poles that look like n1 something something, and so this is the forward limit that we're talking about, right? So as I shift n in the direction n minus 1, somewhere abn1 is going to be 0. And that's where I have an interpretation in terms of the forward limit, right? Exactly where abn1 is 0, that's where I have interpretation in terms of the forward limit. So here I have n1 and ab. And so what is this GL2 integral doing? This GL2 integral, so remember, at this point, this Zn is Zn hat. So Zn hat has been deformed to lie in order to make this, in order to put us in this configuration. And I'm doing this integral. This point here is exactly the point a hat. That's exactly where the line AB intersects n minus n1. Okay? And so the GL2 integration is done for A goes to B on the line AB as usual, and taking the residue at A, sorry, let me say B goes to A equals A hat, and taking the residue there. So in other words, when I do the GL2, I'm moving A and B along this line to that intersection point. And this intersection point exactly is A hat, where AB intersects n minus 1, n1. Remember, Z hat n itself is where n minus 1, n intersects yeah. So. Okay, so all of this sort of just makes sense from the picture. N hat AB and oh, sorry, and I didn't, sorry, that's what the forward limit looks like. That's what A hat is. And N hat AB, that's where Zn hat ends up being. And where is Zn hat? Zn hat is, this is, which I'm calling N hat AB. This is exactly where n minus 1, n intersects AB1. That's exactly the, as I'm moving n minus 1 n, as I'm moving n along the line n minus 1 n, it's exactly when it lies on the plane AB1 where this configuration becomes possible, where Zn Z1 intersects the line AB. Okay, so it's clear on the forward limit, these are the objects that we're supposed to encounter. There's only one thing which is sort of off about this. We're missing the k. The k is too low by 1. Just like the k was too low by 1 in ordinary BCFW, right? We have this extra bracket that tells you where you are on the factorization channel. Well, it's exactly the same thing here. The analog of where you are on the factorization channel here is precisely encoded by this R invariant. So it's precisely the same. Okay? Beforehand, we had n minus 1, n1, jj plus 1. Now it's n minus 1, and the factorization that we're seeing for the forward limit is when n1 intersects AB. Okay? So that's at least the motivation. Now, in principle, you can derive this. It's not so hard, but you can really derive it from original momentum space. You can write things in lambdas and lambdas, integrate over the internal etas, transition down to momentum twistor space, and get this slightly, somewhat complicated looking, slightly fancy expression. Here I've just given you the answer and motivated all the pieces just so you see. So let me summarize again. It's exactly the same as at tree level. You have a piece that tells you what things look like on the factorization channel. Here the factorization channel was when n hat 1 intersects jj plus 1, where n hat was n shifted in the direction of n minus 1. Okay, so all of these intersection points were just coming from lying on that factorization channel. Here, the factorization channel is when n hat 1 intersects AB, right? So AB are these two extra points, and so that's what we're seeing. Everything here is just telling you what n hat is and what this interesting point A hat is associated with the factorization channel here, which is this forward limit picture. Except that we have to get rid of the dependence on the points A and B separately and only remember the dependence on the line AB. And that's what the GL2 integration is doing. Okay. And in both cases, there is some extra factor that tells you where precisely you are on the factorization channel. Okay. And it's just the same factor in both cases. It's just that here it's n minus 1, n1, jj plus 1. And here it's n minus 1, n1. And the role of jj plus 1 is played by AB. Okay. But this formula, you could sort of then gives you a concrete recursion relation for any number of, for any n, k, and l. Okay. And that's the thing, was, as I told you, has been implemented in Jake Bergeli's Mathematica code. And if you want to know the answer for n equals 4 super Yang-Mills to some pretty high multiplicity and pretty high loop order, you can actually get the answer for the amplitude and for this loop integrand just by following this recursion. Okay. Next time I will I'll just say a little bit more about this and connect to something that we've foreshadowed early in the course. Go back to the amplituhedron and describe how everything is defined purely in momentum twistor space in terms of these topological ideas, winding numbers, and so on and so forth. And then for the last few classes of the course, depending on how far we go, we're going to switch gears completely and talk about similar objects in simpler settings. In phi cube theory, if we get there, maybe even in cosmology, where we'll see analogous geometric structures as we've been seeing here. OK, thanks.